Okay, so welcome again to the UN Women AI School Expert Talk series. Today, as mentioned before, we had two different expert talks. The first about AI and storytelling is already finished, and we are now digging deeper into the second expert talk of the day, which is about data, information, and impact. Together with us, we have Dr. Vijay Somanath, an expert data analyst, but I'll leave the introductions as well as the moderation to our member of the steering committee of the AI school, Kirti Jayakumar. Kirti, the floor is yours.
Thank you, Federica. Hello, everyone. Welcome to our second expert talk for the day. I know some of you have stayed with us right from the morning. Thank you for being here through this time. And for those of you who just joined, welcome. Before we begin, feel free to turn on your captions if it helps your engagement in today's session. This is Expert Talk 8, and we have an expert, Vijay Somanath, taking us through a session on data information and impact, where he will give us an introduction to data, data exploration, and best principles for data creation. Without further ado, let me introduce our speaker. Now, Vijay is a data scientist with a strong background in predictive modeling, data analytics, data mining, and data visualization. He has experience with risk management and fraud prevention and works with natural language processing and large language models in the generative AI space. He's passionate about climate and environmental issues and focuses on the ethical and environmental costs of developing, deploying, and using AI. To our participants through the session, feel free to keep your questions coming using the Q&A feature. So this will help us bring it back to Vijay's attention when we do the Q&A session. With that, over to you, Vijay.
Good morning, everyone. Thanks, Kirti. Thanks, Federica, for this opportunity. Uh, Let me just get straight into it. So, I always like to start sessions or discussions like this with this little vignette or a story. And it's also personal because it's one of the first real life examples I saw when I started my own data science journey. So the situation was this: it was 2015, and there were a couple of data analysts working for this huge financial organization, which gave out a lot of financial products like everything from insurance to credit cards. And they were charged by the authorities for securities fraud because they used their knowledge of credit card usage, and and could from that, just from that information, they could say which companies were seeing a lot more sales and hence are going to have a much better quarterly earnings report. And they use that information to make bets in the stock market, and they made very handsome profits. And this always struck with me for a very long time. So let's take this and take a step back and just look at what lessons we can take from this incident. So the first thing is, of course, we hear this being said all the time: data is valuable. But here it actually was, monetarily valuable to the analyst, because not only did they have access to data, they could also mine the data, ask it the right questions, make the correct uh, you know interrelation relationships and connections to the real world, and also to data which is outside their system. So for example, in this case, the data that they had was credit card transactions, but they could make a meaningful association with the data that they don't have, which is stock market movement based on sales reports. And they could make a very meaningful connection, and they could actually get a lot more worth out of that information. And that kind of leads us to the second point on the screen, which is the interconnectedness of systems. I'll have another example coming up shortly on this. Uh, so, a very good, data has data shall set you free, as there was this one very famous line, and there's also another line that's all often quoted in the total quality management world, which is completely on data and quality, which is, in God we trust, everyone else should bring data. And if you can, ask data the right questions and make the connections very, you know, prudently, you can get a lot of information out, a lot of value out. And the third point on the screen also talks about responsibility. Now, just because the analyst could make that connection doesn't mean they should have, which is why they got charged. And so, responsible usage of data covers a lot of different facets. We will be covering a little bit of that also going forward. uh, it can range anywhere from appropriate usage, fair usage. It can also be, uh, you know it should not be, the data access itself should not be of questionable nature, and the way the data is managed, it should not underrepresent or overrepresent anyone, and the way the data is put to use should also be in a very responsible and ethical manner, which is what the last point covers: the importance of data governance, covering access, usage, and documentation. So let's get into some basics. What is data? Anything is data, and our five senses are collecting data all the time. Our eyes are collecting visual data, our skin is collecting sensory data. But in the terms of a machine, a computer, if you're going to interact with data through a system, uh, the system has its own sensory information, which is numbers, labels, text, image, and audio. So a data set can have just a numbers, it can have numbers with text, it can have numbers with images. So it can be a very good combination of any of these things. uh, and a data set can describe what is currently happening, or it can describe an entity, it can describe a relationship. So, if I could give examples for, let's say, characteristics. If you collect information about a flower, a bunch of flowers, and their uh, width of the tepals, width of the petals, which is actually a very famous data set in the statistics world called the iris data set. And it just describes the characteristics of a particular flower of a particular species. uh, then you have entities, so let's say you have uh, a company. So what are all the data points that can kind of describe a company? So you can have the number of people working there, the number of offices that they have, or what is the kind of business that they do, what is the kind of what kind of their inventory, so on and so forth, and so on. And you have so many other things. So for example, states. So if the machine is in an on state or an off state. So in the Internet of Things, which was a buzzword like 6 or 7 years ago, you have sensors. These days you have smart TVs, smart fridges. So all of them have sensors that describe the current state of any particular component. So like I said, we have interconnectedness of these data points. So, for example, just take the one in the middle, which is rainfall data. So, what can you do with just rainfall data? You can plan for crops. You can say, this particular crop needs more water, more rainfall. So, if the rainfall is expected to be more, we can plant this kind of crop. So, you can plan for crops, and you can plan for weather patterns. This is actually a very big field of study in the meteorology area of science. And then you have water resource planning. In cities where there is often flooding in the monsoons and droughts in the summers, rainfall data can really help water resource planning. And for a longer term, climate change patterns can also be studied from the rainfall data. And you can also plan for disasters. If the rainfall data kind of can be used to predict or forecast disasters or cyclones or floods, you can make plans for disaster relief also. So this is just one piece of information, and if you can make the correct connections and ask the right questions, you can plan for so much. So, and this is just 5 examples I'm giving you. I'm pretty sure if you add it to so many other things, you can plan or make room for a lot of different things as well. Uh, so let's talk about another example. Um, this is again, I'm going to use examples to introduce concepts so that we can dig a little into them. So in October 2019, researchers were studying an algorithm that was being used in American hospitals. And this algorithm's task was to say which patients for a particular hospital may need or require additional medical care. And one of the inputs that the algorithm used to make this assessment was the money that the patient has already spent on medical care. Now, so far so good, right? There is nothing, at least according to the algorithm's views, there is nothing that looks off. But when the researchers found you know the kind of profiles of people that were getting benefit out of this algorithm, it was overwhelmingly white people and over black people. So what was happening here? Now, algorithms no longer can use race or demographic information to make predictions or assessments or approvals in this case. This has been the practice for a while now. This has been, the result of, uh, awareness and sensitivity towards using these variables or demographic information in algorithms. So this algorithm does not really use race, but what is it? It is still impacting black patients adversely. So what's really happening here? It's because it is relying on another factor closely linked to race, which is the patient's healthcare cost history. Uh, so what was happening is black patients, when compared to relative to white patients, do not have uh, as good a high income. So when you don't have high enough income, you do not have the capacity or the capability to actually spend money for medical care. So it's not that black patients were not spending on medical care because they were healthy. They were not spending on prior medical care simply because they could not. Now the algorithm could not know this by any stretch of imagination, because the people who model the algorithm did not take this into account, which is neatly kind of getting us into the next part of it, which I wanted to cover, which I think would be the highlight of the session, which is bias and mitigation. So race was not a variable in the model, and yet it still affected black patients. So what is happening here is the bias that is inherently present in the real world, the outside world, it gets reflected in the data. So unless we are conscious about this, unless we take conscious efforts to maybe address this issue, or at least accommodate for this issue in the data set or in the algorithm, uh, stuff like this is keep going to happen. Uh, so, another example I would like to give is let's say you're collecting data and you want to see how many women are taking up more and more STEM courses. Now, if you just go about doing it mechanically and you're not going to account for real world realities, you're not going to get very far in your data analysis. Because let's take certain places and parts of the world where women are not allowed to even have a formal education for various reasons. It could be societal reasons. It could just be the fact, due to the fact that there is not a lot of economic mobility, upward mobility, and so they could not even just afford a good education. primary education, so obviously they're not going to be present in the STEM fields. So if we are not going to address these issues, the data set is going to be skewed in favor of certain countries over certain others. So the idea is, when we are talking about, at least in this example, when we are talking about countries which have low participation of women in education and research, the data set should be tailored, or it should have a different structure as when compared to a similar data set for societies or countries where there is more active participation of women in the education sector or in the research sector. So this example also is basically the impact of real world bias creeping into data. uh, you know a, a, a person collecting data may not actually need to be biased to be having a data set that is biased. The real world is full of imbalances, it is full of disparities, and it should not surprise someone that that imbalance or disparity gets reflected in the data. So that's basically how what bias is. And I have linked this here. The biases are numerous in nature. According to some research, there are over 180 different types of biases. And when you compare any one of them and you put them in the field of data sets or collecting data, the effect is going to be compounded, because you are kind of abstracting the information from the real world into a grid of numbers. And so a lot of nuance does tend to get lost. So we need to be a lot more deliberate and a lot more careful while we are constructing data sets. So how do we ensure inclusivity in data? So when we talk about collecting data or a data set, we need to first define the goal of the data set. Now, what is this data going to do? What problem is it going to address? What research question does it attempt to solve? So once we have that information, then we can actually uh, look into how inclusive it is or how exclusive it is. We can actually have a look at the kind of people that may be impacted by this data if it's not collected properly. And so with that, we can maybe define clear inclusion goals. So for example, in the hospital case, um, they had basically you know the hospital was obviously trying to optimize for effectiveness. They wanted to prioritize patients who may need additional care first. So they were just trying to prioritize effectiveness. But uh, they could have, in the terms of defining clear inclusion goals, they could have also said, how is this algorithm or how is the hospital going to address the fact that there are people that get left out of healthcare covers. Now, engaging diverse stakeholders. So this is important. Now, all of these steps that you see on the right here are constant endeavors. They are uh, never ending. You should have regular and frequent discussions on each of these, so that inclusivity is, it's a journey. It's not one and done. It's a journey. So engaging diverse stakeholders is also going to help, because uh, our worldviews, our knowledge, our impact is defined by our experiences. And so you should always have people from different backgrounds, different experiences weighing in, so that inclusivity becomes part of the process. And then ensuring representative sampling. uh, I'll cover sampling in a second. So basically, sampling is a way of collecting information. And if you don't cover your sampling techniques very well, so it is possible to have more samples from just one class. So we might have all seen the fact that certain um, touchless faucets in the US did not work very well for black individuals, but they worked well for white individuals. This is due to the very simple fact that when the faucets were made, they were trained on data to recognize hands, and most of those hands were, uh, of white people or people with lighter skin. And so when a person with a darker skin tried to use the faucet simply would not turn on. And we also see something. So this was, I would say, not very critical, but sometimes facial recognition algorithms, if they are trained overwhelmingly on black individuals, they are more likely to tag a black individual to be a suspect or a criminal than a white individual. So that is, again, the samples are not representative. So you need to have representative samples in your data set so that everybody gets covered, which nicely leads to audit for imbalances. So we need to have uh, frequent audits that corrects for these imbalances. So I think uh, it was one of the earlier iterations of these image generation models. If you ask the model, if you prompted the model to generate a picture of a successful CEO, it was mostly a white man in a suit. Uh, this is despite the fact in 2023 or 2024 there were very many women CEOs or CEOs of color, persons of color as CEO. So you have all of these imbalances going into the input data. So we need to have audits for these imbalances so that you uh, kind of address them, and then you should document these efforts. So not as a checklist, but as a fact that this happens for this iteration of the data set building. These inclusivity efforts were planned. So if there was anything that's found lacking, we can actually go back to these documents and we can see what can be improved. And then finally, when we have people offering annotation services for these images, we can ask them to include so many culturally sensitive guidelines. So annotation experts are basically people who are brought in to uh, add labels to data so that it describes what the data does or the data point does. So instead of just saying maybe a person listening to music, you can also describe the person. You can say if the person is is a person of color, or if it's the person is a male or a female, uh, or if the person is disabled. So you can have a lot of different ways of being sensitive and respectful to the person as an individual rather than just as a data point. And that is ultimately what this whole thing about bias in data becomes. Um, it's a very fine balance between considering the individual and considering them as a data point. They are a data point, yes, but their individuality should also be respected. So let's talk about data sets themselves. So, on the left, you have a couple of points here, which basically describes the life cycle of a data set. The first step is the planning and the designing stage, which is, like I said, what is the objective? What problem are we trying to solve? And then we identify the data sources. And then the second step is to collect and to create data and data sets. So what are the different data collection methods that we can use, and how do we identify the data sources, and what are good data sources for our specific problem? And then we share, publish, and reuse the data. Once we collect the data, we have to sort of look into how are we going to share this data. Are we going to publish this data? How reusable this data is? So, for example, if you are an organization and you're collecting data for your specific business problem, you cannot share that data publicly very easily. It's restricted information. Whereas economic data, for example, that's open data, so anybody can use that data to make their own extrapolations. And data security is also a very big point. Um, and then storing and managing data, support for further work on the data should also be relevant. uh, because once you finish working on the data, the data set might be become useful for an allied research question, or somewhere down the line when the same problem comes up but in a different dimension. So storing and managing data is also relevant. So through all of this, whatever we covered in the previous slide, which is reducing bias and ensuring inclusivity, all of these steps, all of these stages have relevant steps to reduce bias. uh, and now on the right, let's maybe, if you want to get a little bit technical, which basically talks about the kinds of classifications of data that you may have, and which is directly allied to what we see on the left, which is the first is primary versus secondary data. So primary data is when you collect the data points yourself directly from the source. Secondary data is when you collect them from existing sources, or when you just take an existing data set and you modify it for your use case. And then you have structured data, which is the most common. That's what most people imagine to be data when I say data, or when anybody says data for that matter. So it is usually presented in a grid or in a table. It has easily defined fields. You can easily find things on that. So it's organized, easily searchable with defined fields and defined results. Unstructured data, it does not conform to a predefined format, and it is not easily searchable. Now, what can be unstructured data? It can be, all the tweets that were sent out within, let's say, a specific time period, or it could be all the messages or all the comments that a product on Amazon gets in the review section. So you don't really have any structure to it. Uh, so that does not really conform to a predefined format. Now you can give this format, you can give this a structure, you can give this a format, and then make an analysis out of it, and that's a whole different area of study. But on its own, the data is unstructured. And then you have observational data, but where you just simply record what you see, or what is happening. Or you can have collected through experiments, where you can make something happen and then you collect information out of that. Static data is, it doesn't change after collection. So for example, if at a particular point in time, you looked at the number of people in a country, which is a census snapshot, it's not going to change 10 years from now, 10 days from now. It doesn't change at all. It's static. Whereas dynamic data, it keeps changing. So weather, for example, it keeps changing. Sensor data on IoT devices, that keeps changing. And then finally, you have a buzzword, which is big data, which is just basically a large, ever flowing stream of data, which is always happening. So very good example would be the number of reels that get uploaded to Instagram. So content is always getting generated. So you have a very large complex data set, that is big data. Small data is a lot more manageable in size, and it is not as frequent, and it is not as diverse. Uh, so that was data. Now let's spend a little time talking about some best principles and best practices when we talk about how to manage data sets. So on the left, you have the FAIR principles, which is findable, accessible, interoperable, and reusable. This is mainly focused on how to prepare your data so that it can be reused by others. So this is all about having, so what you have collected your data, After that, what are all the principles that come into play? And so you have to have answers for all these questions, the questions that I'm about to tell you, throughout, from the data collection process to how we are going to store and manage. Now, there's a difference between findable and accessible data, and just the way FAIR principles describe such a data set, to just open data sets. Now, for example, open data sets are just there on the internet in the public domain. They are accessible and free to use for literally anyone and everyone. Whereas accessible data, in terms of FAIR principles, it basically talks about regulating access. It's not uh, closing off access. It is a more responsible usage of data, I would say. The person is identified, their intentions are their their intent to use the data, what is their research question, all of that is give taken in, and then the data is made accessible. Findable is basically the data should not be hidden in a folder somewhere in the dark corners of the internet. It should actually be findable. People should be able to get a link to that very easily, at least to know what the data is about, if not to the full data set. Interoperable is when we create a data set and it should kind of work with existing data sets, or if a new data set is about to come up in the future, that data set should also find you know interoperability or just usability with that existing data set. And reusable is, you know the data should be good for the future also, with the, of course, with the necessary caveats. But if the problem were to be needed to be studied again, this data should provide value to that research at that point in time as well. So that's fair. Care is more related to the indigenous and marginalized communities' intentions and their well-being. So care is basically standing for collective benefit, authority to control, responsibility, and ethics. So all of these 4 points are basically for the benefit of indigenous and marginalized communities, or should have the benefit of indigenous and marginalized communities in mind. So let me just take it through an example here. So on the left, you have the stages of data collection, and then you have fair and care principles, and you have bias mitigation. So I'll leave this deck with uh, uh, with people to just go through. But basically, this talks about all of the things that needs to be done for the fair principles, for the care principles, and for each stage, what is the necessary bias to be mitigated, and how we plan about doing that. And this actually has a couple of extra steps, which is towards the end: archival and destruction. Sometimes data sets, they may need to be archived if they're no longer relevant, or they may need to be destroyed if it's controlled data. If it needs to be protected, if identities need to be protected, or if privacy needs to be protected. And so these are fair and care principles along with bias mitigation methods. Now, beyond this, also, we have in the real world legal frameworks to obey or to have in mind while we handle data. For example, the GDPR, which is a law in the EU region, it talks about how companies or organizations that use data or that interact with data, they need to protect PII, which is personally identifiable information. So you cannot use a person's name or a likeness or any piece of information that can be used to identify a person. We have to anonymize that. So you have basically those rules set in place for privacy. And so uh, you also have certain laws that say data collected in a particular country has to be housed in that country. The servers housing the data need to be in that country, and it cannot reside outside the country from where the data was collected. So there are also laws that talk about that. And so, the, while it is, it's more of a hygiene item, I would say. You have to follow those rules and regulations. These are best practices. There is no law that says, at least to my knowledge, that you have to do these things, but these are best practices which makes your data set more holistic. It looks at the problem more holistically, and it can also solve the problem more holistically. Now, let's look at data analysis. Let's get so the coming slides will take us through what data analysis looks like. So you have, usually data analysis is considered to be of four different types. So this is from increasing complexity from left to right, I would say. Uh, Descriptive is what happened, exploring. So the data is collected after the event or after a particular state, and it basically describes what has happened, uh, and it figures out patterns, so on and so forth. Diagnostic is why it happened. So you go back to root cause analysis, you go back to correlations and relationships. And then predictive, so it has happened, whatever has happened, so what could happen next? So that depends on the patterns and assumptions unearthed in the diagnostic and the descriptive sections, and you're basing on that, you're extrapolating and you're predicting future states. And prescriptive is, for these future states, what should be our response. So that's where you come with optimization and simulations and so on and so forth. Uh, so let me just talk about exploring data for now, because diagnostic, predictive, and prescriptive are can get little. We may not have the time to go into all of that. So exploring data. So on the left, you have a table, which if you just look through it, uh, even by just eyeballing the data, just looking at it with your eyes, it looks like the data sets, 1, 2, 3, 4 are very, very similar. And if you do calculate the average of the y's of all four, you are likely to find that the averages and the medians are very close, if not the same. But on the graphs, you see that the patterns that they exhibit are very, very different. So this is basically what this is, hardly around 15 lines of data, and just 15 lines of data can you know hide such an interesting pattern. So this is the Anscombe's quartet, and the reference is linked there. So you know this is these two are, I would say, closer. These two are completely different from all the others, but even within these two, the line of best fit is better here than here. So what does this tell us? This tells us that visualizing data is a lot more powerful, and a lot more engaging, and it's a lot more, I would say, even time saving than just poring over reams and reams of data like this. Now, that much is obvious, which is why we have a lot of graphs, we have a lot of charts and visualizations everywhere. And, you know, this kind of brings us to what else is possible. So, EDA, which is exploratory data analysis, has a few aspects here. So EDA aspects of understanding data structure and data types. So you can identify patterns and trends. You can detect anomalies and outliers, and then you can also assess data quality and completeness. So what that means is you can say if the data is complete, if certain observations have data missing. And then anomalies and outliers, you can say which of the data do not conform to usual patterns. So, for example, if you were to chart the rainfall history of Chennai, you would see that from 2015, the rainfall data has been high, especially in the months of December, because since 2015, Chennai has been having flood-like situations every December. And so if your graph started in 2014, it would mean that the data looks normal. There is no outlier. But if you stretch the time long enough, you would see that the trend started only around 2015. So is that an anomaly? For 2015, it is an anomaly, but we are in 2025 now. It's been 10 years of that. So it's no longer an anomaly. So it is no longer an outlier. So we have come to expect this to happen in December. So that was just, that's an EDA aspect. So what are EDA techniques? So you have visualizations, and basically you have very different types of graphs. We have a showcase session on visualizations, and there are many kinds of visualizations, each for a different problem statement, each for a different type of insight. And then you have calculating descriptive statistics, which is very basic, your school level mean, medians, modes, correlations, and so on. And then checking for missing or duplicate data, and then grouping and filtering data to spot patterns. So this can be anything from simple bar charts to more advanced techniques like clustering. And then EDA elements, like I said, summary statistics, the standard deviations, and your averages and your medians. And then data distributions are, do they follow a bell curve? Do they peak sometimes? Do they dip sometimes? And relationship between variables and missing values. And then this other checks is what is very important for ensuring that there is no unconscious or inherent bias in the systems. So you have class imbalances. Class imbalances are basically one class or one category being underrepresented. So if the if you're talking about examples, we can say the example of women being underrepresented in STEM areas. So that can be a class imbalance. So you have to adjust to that class imbalance which exists in the real world in your data. And then you have temporal patterns, which is basically time series data across time. So one of your axes is just a unit of time, and you're tracking the movement of another uh, pattern over time. And outliers, like I said, what does not conform to the usual pattern of data, that is an outlier. So with that, let me jump to a showcase. Um, so this is a profiling report. Uh, so this describes a data set which is a very popular, very open data set, I would say. It is called empty cars, and it describes a series of cars with just information on uh, their uh, their variables that is relevant to cars. So this is basically a profile report generated by just 3 or 4 lines of Python code. So all I had to do was load the data and ask Python for a profile report, and it gave me this very nicely formatted HTML. So let's have in the overview. We have the overview here. So you have 11 series of variables, and then you have 32 rows of data, and you have no cells which have any data missing, which means there is no data point which has a missing value, and there are no duplicate rows, and so on and so forth. And you have 7 numerical data points and 4 categorical data points. So categorical is basically something that describes a data point, whereas numerical is basically a measure of data. So you have all of these variables. mpg is miles per gallon, and then CYL is the number of cylinders. So if the car engine has 8, 4, or 6 cylinders, and you have all of these uh, variables, you can easily see what kind of distributions they have, what kind of minimum, maximum, what is the average value, so on and so forth. So you can basically see what each data point is going to look like. And the categorical, since you will not have the distributions there, you just have the count presented as a bar chart. And then you have interactions, which is very important. So you have the number of carburetors and the number of and the miles per gallon. So if you know anything about cars, I certainly don't. They should tell you something. But basically, you can actually have a look at what for what number is what number of carburetors going to be relevant. Um, and then correlations. Correlations is a fascinating field of study, and there have been endless discussions and endless examples that say correlation is not causation. Basically, what that means is as one value increases, another value increases or decreases. Or put more simply, uh, the proportion of change in one value causes um, corresponding change in another value. So simply because that happens does not mean that this is caused by this or this is caused by this. So correlation analysis is a very important EDA step, I would say, because it tells us of what to look for in the data and what kind of associations can be made between the data points. And missing values, since we know there is none, so this graph is all blue. If there were missing values, there would be red streaks in these blue bars. And then you have a sample. And all of this is possible with just 3 lines of code. And it is going to tell us everything, a lot of things that we may need to know about this particular data set. Uh, and for another showcase, I would like to take us through a Tableau workbook. So Tableau is uh, one of visualizing tools that are available. It's very, very no code. You can code to it. You can create your own custom metrics. So for that, you may need to write a little bit of code. But for example, for the most part, you don't really need to code. And there are other tools like this. You have Power BI, ClickView, so on and so forth. But just for the case of the showcase, let me just show you how to use Tableau. So this is Tableau public, which means anything I do is being saved publicly. If I need to use the data locally in my own machine, I will have to pay Tableau a license. So what we have here uh, is basically, 1 second. Is a very popular data set in the Tableau world called the Superstore data set. Oops, sorry. Uh, all right. Apologies. Let me just move on. So Tableau is basically, like I said, it is one of the tools that is basically used to visualize data. Uh, you have other tools, like I said, MS Excel. Most people don't use MS Excel for their slices and their pivot tables, but if you can use them, you can have some really powerful visualizations. Power BI is also from Microsoft. You have Google Data Studio. And for data ethics, you have Fairlearn, Equitas, and WhatIfTool and AIF 360. Now, AIF 360, Fairlearn, etc., are deep learning tools which basically talk about algorithmic bias, and they are far more complex to use, I would say. and they talk about inclusivity in the algorithmic space and not just the data level, and data cleaning and prepping, which is the very first step. So you have collected data, so now you want to clean it up before you can start analyzing. And it doesn't matter if the data is structured or unstructured. 80% of data analysis or 80% of data scientists work is data cleaning and prepping, because uh, the data is already going to be there. So we need to make it presentable or readable in a way which helps us to solve the problem we're addressing. So it needs to be in a certain way for that, for the algorithm to use, for the tools to use. So these tools help you do that. And for the most part, none of them need code. And beyond this, Python is a very popular programming language, and they have a lot of tools and libraries to support all aspects of data operations, right from exploring to model building. And model explainability is also important, which is once you've built the model, you need to have the ability to explain why the model made the decision that it did. And that's a completely different and a very relevant but completely different area of this whole aspect. So it also has key concerns like inclusivity, bias mitigation, and harm avoidance. Uh, and that's basically it. I think we are at time. I'm happy to take questions.
Thank you so much for that rich and insightful presentation, Vijay. It was absolutely amazing to get to listen to you. We do have some questions, and you're right, we are close to time. We've got about 8 minutes. So I'm going to invite you to answer the questions, but perhaps with about a minute or two on each question. So the first
Right.
question we have is to check or counter for biases, we often have our assumptions that we work on, but these assumptions could be wrong or not previously explored. How would you suggest countering biases in this case?
Okay, so that's a very good question. So here, when you're talking about clearing out biases before even talking about data, so what we need to have, like I said, is engaging diverse stakeholders. Okay, so when you sit down to discuss data collection strategies, you should have the inclusivity goals clearly laid down, and you should also look at uh, you should also have a discussion on what each of us feels is normal, because what is normal to one person is not going to be normal for the other. And so once we have those discussions, we will find out the unconscious biases that we have. And once you identify the unconscious bias, that is half the problem solved. So once you move on, how you move on from that is, okay, how do we address this unconscious bias? And how do we collect data that does not fall into this trap?
Amazing. Thank you for that, Vijay. So our next question is how to determine the baselines or start point for data collection. I understand it depends on the need, but if we want to study long-term patterns, such as the flood pattern in Chennai, as you mentioned, how would we do that?
Okay, so each problem will have a different way of approaching it. So, for example, if we're talking about weather data, we can definitely look for open data sets. Meteorological data sets uh, are easily available. Now, meteorological data sets are very complex, and you cannot collect them on your own. So, data collection by an individual is not going to be very easy. So, you need to have specialized tools. You need to have institutional support for that. So, like I said, it like with the question, the person who asked the question themselves said it's going to depend on um, the problem statement itself. Uh, but a very good point to start would be to see how existing data sets for the problem have been collected, and try to see if any of those methods can work for you.
That leads us to our next question, Vijay. Thank you for that answer. Our question is from Imad. Where do you recommend participants go to get free quality data sets?
Okay. Again, like I said, this would depend on what kind of data you're trying to collect, what problem you're trying to solve. But for me, as a data scientist, even in my student days, getting to find data has been, uh, you know, possible only for very specific problems. So, for example, if I wanted to get a data set on uh, very mathematical or data sciencey aspect of it, I would go to places like Kaggle and Hugging Face, which is now a very good source of data for deep learning or AI ML models. Uh, Beyond that, I think a lot of universities have collected data for a lot of different studies. So, for example, you would find for economic data, you can go to uh, you know places like the Reserve Bank or the Bank of England. You can collect data or economic data from places like the Economist. Of course, you might have to pay a fee to access those data points, and University of I think MIT has a lot of data sets. University of Chicago has a lot of data sets. University of Stanford has a lot of data sets. Again, these data sets may not really address the question that you're trying to solve, in which case you will have to maybe create your own data set. And one thing that I kind of missed to mention, but I think it makes a very good point to mention here, the way you collect data should also be fair and ethical. You cannot basically steal data. If there is copyright involved, you have to give credit to, you have to give respect to the copyright. You have to, uh, you know, make sure that is addressed, and you cannot let anyone feel exploited for their work.
It's almost like a script writing itself because your answers are leading beautifully into the next questions that are coming in. Now, I'm going to just give you the last question, Vijay, and then hand it back to Federica. This one is from Alex, who says, I'm a computer science student and most of my experience is related to data science and or machine learning. What can I do to make my work more equitable or contribute to responsible data practices?
Okay. First off, congrats on choosing computer science and all the very best. How to make it more equitable is, well, that's a very long answer, Kirti, but to keep it short, I would say, uh, personally, I am thankful for this opportunity. I would love to volunteer my services. Maybe just spread your knowledge, spread your learnings, uh, and volunteer your time, volunteer your efforts. Uh, and then how to make it more equitable is basically, you should try to look at problems more equitably, and try to pick up problems where you can make an impact with your knowledge and your time. So for example, just to give you a very small example, I would say, use local LLMs, support the community developers, contribute to open source projects, and make sure that you stay up to date on where biases and exclusions are harming people, and you can maybe make identify efforts to stop or mitigate those areas. But yeah, I think the open source community is excellent, and I think you should consider contributing there.
Thank you so much, Vijay, for your time, for this amazing presentation that was detailed and tackled. Yes, Alex, very quickly.
Hi, I'm the person who asked the question about like how I can make my work more equitable as a computer science student. Like, if you're not running out of time, like I was wondering if you had any recommendations about like what open source projects like are like good to contribute to in like this respect.
Or
Um
Or we can also, if you have a list, Vijay, we can add them into the additional resources. What do you think would be best?
Sure, I can put up a few links. I can share them with you, Frederica. Will that be okay?
Perfect. Thank you so much. This will also allow participants who want to double check it at a later time to do the same. But thank you, Alex, for the question. And this goes also into also showcases the importance of these expert talks and the reduced time and the importance of looking at additional resources. So thank you, Alex, and thank you, Vijay. So again, Vijay, thank you not only for answering this question, but for the whole presentation. As I was saying, you tackled very technical aspect in a very clear and understandable way that I think will benefit our participants, especially because now, as many of you may know, we are in the preparation of the high school grand challenge, which will ask them to leverage the knowledge and skills they developed throughout the high school for developing their solutions. So today's expert talk will also be important for those of you participants who want to build their own AI models and solutions, and especially will provide them with more information about how and why and where to find the right data and how to assess and evaluate them and explore them through an unbiased and unbiasing lens. So thank you again, Vijay. We'll keep in touch. Thank you for your time. I also know that you took personal time off from work, so this was truly amazing. And I hope that we will have a chance to see each other and collaborate again pretty soon. Thanks also to all the participants, and let's say that this other expert talk is over. See you next week to all of you.
Thank you. Thank you for having me, and I will look forward to future collaborations also. Thank you, Kirti, for moderating.
Thank you, Kirti, for your amazing moderation. Thank you. Bye.